Welcome to 1.3 Graphs of Functions. Some of this we've talked about a little bit and prior to this section. For instance, the vertical line test for a function. A set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects a graph at more than one point. Therefore, we would conclude, based on this graph, that this is a function However, that is not, because in here somewhere we have a vertical line that passes through more than one point of the graph. So really useful. If we can see the picture of the graph, makes it pretty easy to determine if it's a function or not. Increasing, decreasing, and constant functions. This is such a great case of just learning how to read math, and they can make things sound pretty complicated when they're super simple once we get a grip of it. So going through the increasing one, a function f is increasing on an interval when for any x1, x2 in the interval, x1 less than x2 implies f of x1 less than f of x2. Well, that is a mouthful and doesn't really make a whole lot of sense to me when I think of it that way. But when I think about x's being right, left, put a little graph grid in here. X's being points that are to the right and left, and y's, let me lock in my zoom here, and f of x's, which are fancy, f is just a fancy name for y, these are heights of the graph. Here's what this says. If I have an x value that's left of another x value, the height of the x value, or the height at the first x value, is below the height of the second. So if I've got, let's say this is x1 and this is x2, the height at x1, here's what this says, the height of the graph at the first point is below the height at the second point. Oh, then the graph must be increasing. So we just learned to read this, at least I needed to, because as I probably mentioned in this class, I'm not really a great abstract thinker, and I have to deal with these abstract concepts. So I learned to read this as say, okay, we have a decreasing function if a point that's to the left of another point, the height of it is bigger than the other point. So if the point to the left is higher than the point to the right, the function must be decreasing. And a function is constant on the interval if the height at the first point is equal to the height at the next point. Oh, well, that makes sense. It's constant. We have a constant height. Okay. Definition of relative minimum, relative maximum. This is kind of learning to read math. A function value, the height at point A, is called a relative minimum of f if there exists an interval x1, x2 that contains A. All right, so I've got like an x1, an x2, and somewhere in here I've got an A. If there exists an interval that contains A such that x1 is to the left of points x is to the left, so we're in this interval, implies that FA, the height at A, is less than the height of any of the points between there. The height at A is less than the points, any of the points between there. It must look something like this. Okay, we have a minimum. So we have a maximum on an interval if all the points that are between two, from a left point to a right point, if all the points between there are not bigger than the point at A, we have a maximum. Okay, so what you're telling me is that we have a minimum, we have what's called a relative minimum when the point's at the bottom and a relative maximum when the point's at the top. Pretty simple. Okay, tests for even and odd functions. Here's another one, learning to read math. A function f is even when for each x in the domain, for all my right and left values of the function, the height to the left is equal to the height to the right. F is a height. If we consider x to be a positive value, this is the opposite of a positive, so a height to the left is equal to the height to the right. For instance, if I go 3 out here and it gets me up 5, And then if I went 3 out here, I'd be up height. The height to the left is the opposite of the height to the right. Oh, so what we have here is symmetry over the y-axis. So our friend y equals x squared is an even function. Here's an even function. If I had a function that looked like this, even function. Okay? A function is odd, then how would we say this? Say it to yourself, just as we handled this one. The height to the left is the opposite of the height to the right. So if 3, 2 is on an odd function, the height to the left would be the opposite of the height to the right. The height to the right 3 was 2. The height to the left 3 would be the opposite of that. So what we have is symmetry through the origin. Rotational 180 or symmetry through the origin. So here's a common one for it. Well, maybe this most simple one would just be a line through the origin. Like if this is 3, 5, then somewhere down here this is going to go through -3, -5. The height to the right is the opposite of the height to the left. Another common one, y equals x cubed. Ooh, that was terrible, but I'm not going to redo the video. Y equals x cubed is an odd function. Okay, so there's our definitions. There's learning to read math. Let's go through some examples here. Find the domain and the range of the function. They don't even tell me what the function really is algebraically. I just have a picture of it. So for domain and range, and I'm going to answer in interval notation. That was on the tail end of the 1.2 video. You're welcome to go back and take a look at that, but I think you'll catch on even if you missed it. So interval notation, for when I'm looking for domain is the value, the x values that exist on the graph. And I'm assuming this graph continues on to the right and on to the left. It won't back onto itself because then it wouldn't be a function. Wouldn't pass the vertical line test. Therefore, what we do is we scan domain from left to right. So I assume the graph's going to exist from -infinity, and it continues, it never breaks, to exist until infinity. So we would say -infinity to infinity. We use parentheses by infinities because we can never get to infinity. Infinity is a concept, it's not a number. For the range, we scan, so here we're scanning left to right. For the range, we're scanning the y values from bottom to top. This graph goes down forever, and it's represented on the graph all the way up forever. So it is also -infinity to infinity. And you could say all real numbers, all real numbers. So not the most particularly interesting one for that portion. Then they want us to find f of 0. Well, f of 0, how should we really read that? For me, maybe f of 0 makes perfect sense, but once I go back to here, the height to the left, height to the right, this is asking what is the height of the graph at 0. Oh, the height at 0 appears to be 2. F of 0, the height at 0 appears to be 2. Okay, number 10, scan left to right, domain. Appears like it goes to the left forever. It's coming in, coming in, coming in. Doesn't exist right here, but this picks up the slack for it and then can exist forever. So all reals or -infinity to infinity. A scan of the range, we scan from bottom to top. That's the y values. The graph does not exist until we get up to -3, and it appears to exist at -3 bracket. And then it goes up forever and even doubly exists here, so through infinity. So this is equivalent to saying y or f of x is greater than or equal to -3. But interval notation, we'll be using that regularly. You'll see quite a bit of that in the near future. Okay, finding domain and range of the functions. Use a graphing calculator to graph the function and estimate its domain and range. Okay, I don't think we need that for this one because we ought to be well equipped to handle the graph of this. It's x squared down 1. Maybe we're not well equipped to handle that one, but with the graph of this one, I'm just going to, without going to calculator on this, and say it looks like that. So we're going to use the graphing calculator to graph the function and estimate the domain and range. The domain appears like it is all reals, goes to the right forever, goes to the left forever. However, the range only exists from -1 to infinity. -1 including up to infinity. That happens when x is 0. And we're going to do enough of the algebraic. Okay, so let's go ahead and take a look then on calculator. Clear this guy out. Let's take a look at this next function. So we've got square root clear of 4 minus x squared. And I'm going to zoom 6. That's standard. Hopefully we didn't just lose our image there. Okay, and let me reset this so we get a little bit better look at that. Darken it up a little bit here. Okay, appears as though it goes from -2 to 2, and I might want to just do this. I might just want to hit trace and put in 2, and I see, oh, the graph does exist there. We got a value at 0. If I put in -2, the graph does exist there. Let's go to, I'm going to go to 2.01. Oh, there is no y value that associates with that. Hopefully you can see that. So I suspect the graph exists from -2 to 2. Now, when we go back and we look at, let's try this again. When we go back and we look at the equation, so this is sort of the algebraic built in, kind of makes sense that 2 would be a point of interest and -2 would be a point of interest. So our domain is from -2 to 2, parentheses or brackets. Well, remember when I put 2 in here, it existed on the graph. 2's not a problem. Square root of 0, no problem. I'll go range. The range on it appears like it goes up to 2, and it would be at 0. I'm going to put in 0 and see where we're at. Yep, we're up at 2. So this graph doesn't appear to exist until I get to 0, and then exists up to 2. Remember, range, we scan from bottom to top, 0 to 2, and it includes both of those in the range. And absolute value, talked about absolute value, but worth repeating because you might not have needed to see an earlier video on that. To get absolute value on your calculator, let's see if I can get this so we can see everything. I'm going to go y equals, clear this out. I'm going to go second and then catalog here. Catalog's down here on 0. And I like that for absolute value because the catalog is all the commands we can get, alphabetical, and absolute value is the first one. So I go enter there, and now I'm going to put in my function. Well, you zoom in and out with our brightness. So I need, oh, I guess before that I'm going to insert, I'm just going to go 0.25 times. You could do 1 divided by 4 if you wanted. And then I'm going to go x minus 5. And I will graph that guy. Okay, so as you can see, it appears like our domain exists forever. Goes -infinity to infinity, or maybe better yet, all reals. Whoops, parentheses, parentheses. And then our range appears like it starts at 0. Now let's go back and check the algebra. It seems like 5 would be a point of interest here. So if I just go trace 5, I get 0. Looks like 0 and on up. So our range is 0 to infinity. So nice use of calculator there to be able to find domain and range, particularly range. Let's go back and talk domain just a little bit of these, because here's how we handled domain before. Can I square any number I want? Yes. Can I subtract 1 from any number I want? Yes. Domain's all reals. Can I square any number I want? Yes. Can I subtract any number I want from 4? Yes. Can I take the square root of any number I want? No. 4 minus t squared has to be greater than or equal to 0. So I just set it equal to 0. Hopefully we see we can factor 2 plus t, 2 minus t, difference of perfect squares. So that's t equals negative 2 and 2. At which point we go to a number line. We'd say, can I put 2 in here? 4 minus 4 is 0 squared. Yep, I can put 2 in here. Can I put negative 2 in there? Yep. Can I put something in between? Can I put 0 in here? Yes. Can I put 3? 4 minus 9? Nope, can't take square root of negative 5. Likewise, I can't put in negative 3. So there we go, negative 2 to 2. Okay. Likewise, can I subtract 5 from any number I want? Yes. Can I take absolute value of any number I want? Yes. Can I multiply any number I want by negative 1/4? Yes. All reals. All reals. Okay, let's continue on. Whole bunch of instructions on this one. We're just going to take it one bite at a time. In exercise 17 and 18, use the graph of the function to answer the question. So we already got this piecewise function. Determine the domain of the function. So domain, again, you see domain, you're scanning left to right. I think the graph's going to exist from negative infinity on forever. So the domain, all reals, are negative infinity to infinity. The range, you see range, you scan from bottom to top. I believe this is going to go down forever. I believe this is going to go down forever. So it exists from negative infinity up to 4. Negative infinity up to 4, parenthesis or bracket. Looks like it's including up at 4, so bracket. Why no parenthesis at negative infinity? Because we can't ever get there. Find the values of x for which f of x is 0. So this, again, how do we read that? Because somebody is going to, on the test or quiz, is going to say this. I'm going to say, find the value for x when f of x is 0, and they're going to say 4. But this says, when is the height 0? What value of x gives me a height of 0? Right here we have a height of 0, so that must be 2. And back here we have a height of 0, and that is negative 4. What are the values of x from part C referred to graphically? This 2 and this negative 4, of course, they're referred to as zeros algebraically, but graphically they're referred to as the x-intercepts. Find the height at 0. Boy, I hope you get used to saying that. Maybe you're great with find f of 0, you know exactly what it means, but for me, f of is a y value. Find the y value when x is 0. Find the height at 0. The height at 0, that's 4. What's that referred to? Of course, the y-intercept. What is the value of the height at x equals 1? At x equals 1, we're right in here, so we're somewhere up in there. How would I know exactly where it is? Maybe it's up at 2. Well, let's look at the function. If I put in 1, 1's bigger than 0, so I get this treatment right here. And at 1, I get 4 minus 1 squared. 4 minus 1 is actually 3. At 1, we're actually up at 3. What is the value when we're at negative 1? How high are we at negative 1? At negative 1, I don't know, maybe we're up there around 3. Let's put in negative 1. Negative 1 gets this treatment because it's less than 0. Negative 1 plus 4, it's 3. The coordinates of the point on the graph of f at which x equals negative 3, x is negative 3 right here, can be labeled negative 3, f of negative 3. Oh, yeah, that makes sense. The x is negative 3, and this is the height at negative 3. Or negative 3 what? How high are we? Well, negative 3 gets this treatment applied to it. Negative 3 plus 4, 1. All right, long problem, a lot going on, but one of those things that you'll hear me refer to a lot of times. It really should just become, if it's not already, a whole lot of simple. Okay, I want to wrap up through 40 here and then split this into 2 videos. We'll be doing this section over a couple days. Vertical line test for functions. Oh, this is a nice simple one. Use vertical line test to determine whether y is a function of x. Describe how you can use a graphing utility to produce the given graph. So this is clearly not a function. Not a function. Now, how could we graph this? Because our calculator wants us to put y equals in. What we'd have to do is take this equation and solve it for y. So let's try that. I get negative y squared equals negative x. I subtract x on both sides, joins a plus 1. Multiply both sides by negative. I get y squared equals x minus 1. And then I would get y equals plus or minus square root of x minus 1. And I would have to graph y1 as square root of x minus 1 and y2 to be the underside of that sideways parabola. y2 equals the opposite of square root of x minus 1. Okay, vertical line test. Looks like it passes all the time. I'm going to put is a function. Not a function, is a function. Passes the vertical line test. We're going to solve this for y. Now notice when I solve for y, we got the plus or minus, and that's a dead giveaway algebraically that it's not a function. So this one, we shouldn't have problems like that solving for y. Let's see. I'm going to go x squared. I'm going to add the 1 equals 2xy. I'm going to solve for y by taking both sides and dividing by 2x. And don't you dare reduce this x with this x squared. This x squared is not a factor of the top. But I didn't have to do a plus or minus situation. That's the point they're trying to get across here. Okay, 23 through 26. Determine the open intervals. Intervals means scan left to right. It's kind of like domain. The open intervals on which the function is increasing, decreasing, or constant. Well, the graph starts by going down and ends by going up. It never really stays flat. It's instantaneously flat here, but then going up immediately. So it is decreasing from negative infinity. See, and it's always x's. I don't want to say it's decreasing from up here to down there. I want to say it's decreasing from over here at negative infinity until we get to 2. And it's really not decreasing at 2. And then it is increasing from 2 to infinity. Not from negative 3 up to infinity, but from 2 on the x's to infinity. Good time for you to try this one. Now, the big question should be, is it constant in here? Well, I can't put 0 in here for x, so the graph doesn't exist through here. Goes down, goes up. Common mistake. It goes down from infinity down to 0 and goes up from 0 up to infinity. Nope, intervals. It goes down from negative infinity over to negative 1. It decreases from negative infinity over to negative 1, and then it increases, and we wouldn't say it's decreasing at 1 because at negative 1 because it doesn't go to the other side. It stops existing there. And it increases from 1 to infinity. Okay, I'm going to wrap up this page. In exercise 27 to 34, use a graphing calculator to graph the function and then determine intervals on which the function is increasing, decreasing, or constant. Okay, more calculator work here. So let's go back on y equals, clear this function, and I am going to go the opposite of x raised to the, and you can put in 3/4. I guess I will. I'll put in 3/4. So you could put in 0.75. And I think I'm in Zoom standard, so I'm just going to leave it there and see if that's enough for us. Maybe we'll need to zoom out. Graph this. Okay. Function appears to quit to start at 0. Maybe I'll do a trace 0. And at 0, we're at 0. Does it go to the left at all? Let's go negative 0.001. It doesn't exist there. The reason that's happening is because this could be written as negative 4th root of x to the 3rd, and I can't have a 4th root of a negative. Can't have an even root of a negative. So not surprising there. Maybe we'd want to go window. Let's see if it looks like it keeps going down as I let x go to 100. And I'm going to go zoom fit when that's done figuring that out. Zoom fit's a nice feature. That's zoom 0. It uses up all the space in the calculator available for our given domain, in this case 0 to 100. It looks like it's going to keep going down forever. So B, determine the operant intervals on when it's increasing, decreasing, or neither. It is decreasing from 0 to infinity. All right, 34 is kind of a cool graph for the purpose of this problem. So I'm going to go back to here. Remember how we get absolute value. Second, 0, that's catalog. And we get absolute. And once again, I'm going to go back in here because I should have put a negative first. Insert a negative. And in here I need an x plus 4. Outside of there I need a minus and another absolute value. Second, catalog. Absolute, and x plus 1, and I'm going to go back to zoom 6. Ooh, there's our constant right there. We get a little constant value in there. So this graph appears as though, I'm going to let you get a better look at this one. This graph appears as though, and let's stop for a second and look at our interesting values. Negative 1 and negative 4 appear to be interesting values where the graph changes. Let's go back and look at this, if we can. Seems reasonable that negative 1 and negative 4 would be interesting values for us. So our graph is increasing as we scan across x from negative infinity, not up to negative 3, but negative infinity over to negative 4. So we're increasing negative infinity to negative 4. And then we appear to be constant from negative 4. Let's see if that's true. I'm going to go trace. I'm going to put in negative 4. And I'm just going to start bumping this over. And you see the y value is not changing. So that leads me to believe it is constant through there. So we are constant, and we wouldn't really say we're constant at negative 4 because it changes on the other side right at negative 4. So we are constant from negative 4 until we go over to 4. And then we decrease from 4 forevermore. So then we are decreasing from 4 through infinity. Okay. Oh, calculator struggling a little bit, staying focused with that, or excuse me, my projector's document camera's is struggling with my calculator, and I'm struggling with English. All right, approximating relative minimum of maxima. This is a huge calculus act that's done quite a bit. Use a graphing calculator to graph the function to approximate the relative minimum and relative maximum of the function. So we're looking for any hills that have a top to them or valleys that have a bottom to them. So let's jump back on the calculator here, clear this out, and let's enter our first function. X to the 3rd, step out of that, minus 6x squared plus 15. Now, I don't know if Zoom Standard is going to do it for this or not, but we're going to give it a try. So I'm just going to go ahead and graph. That looks like I need a better look, but it does look like we have a relative maximum and a relative minimum. So maybe I'll just take my window and expand my y's, my y minimum maybe to negative 20 and my y max to 20. Let's see that. Let's see if that gets everything we need. Well, there's our max. Oh, there's our minimum. Okay, this is a beautiful thing to be able to do. Boy, I can't tell you how much time I spent finding approximating maximums and minimums before without calculator back in the day. Second, calculate minimum. So my minimum's over here. I'm looking for a left boundary. You want to get close, but make sure you don't go too close so you pass the minimum. Step to the right of that minimum, and then hit enter. Assume that that's rounding error. Now, it might actually be accurate, but we're going to assume that's rounding error, and it appears as though we have a negative of negative 17 at 4. So how would we answer that? Use the graphing utility to graph function approximate any relative minimum maximum. So we have a minimum of negative 17 at x equals 4. And then we'll just repeat that for our maximum. Second calc maximum. Again, I want to be to the left of first. Get to the right of it, stamp enter, hit enter again. And 9 times 10 to the negative 7th, that's 0.0000000, negative 9. That's virtually 0. We can assume that's probably 0, 15. So 15 is a maximum. 15 at x equals 0. So use graphing calculator to approximate relative max and min. Good time for you to try this one. You want to pause and come back to it. This will be the last problem I do on this set, so maybe if you've got your calculator with you want to give it a shot. Okay, hope I'm saying welcome back because you went ahead and tried it on your own. Let's go ahead and go back into y equals, clear out our function, and enter this new one. We've got x square root of 4 minus x squared. And I'm going to go back to Zoom standard, which is Zoom 6. Get used to it. There's an interesting little graph. That's one that pops up in calculus quite a bit. In fact, we'll be playing with that graph. You won't remember this probably, but we'll be playing with that graph in the 4th term quite a bit. So here's my thought. I look at that. It looks like, boy, it just seems like the graph kind of dies out at 2. So it's worth taking a look algebraically. Is that 2? Did I enter that right? Let's see. Y equal. Oh, I put an x squared on there. I'll bet you caught that. I'm going to delete this just for a minute. Yeah, I was a little bit surprised by that graph. Let me delete that off of there and try this again. I thought that was the wrong graph. Okay, so now it looks like it kind of dies out at 4. Well, I'm going to go ahead and go trace and see if that's true. 4. And that exists. If I bump to the right a little bit, it doesn't exist. If I bump to the left of there, it does exist. So I believe at 4, it stops. And if we look back at our function, that seems reasonable. Okay, so maybe you want to see if this comes back up at some point. You can zoom out, but this is going to continue to go down forever. So we have an increasing function, then it decreases. All we have is a relative maximum. We don't have a minimum. This is going to try to go to negative infinity. It just isn't ever going to get there, so we can't say that there's a minimum. So I'm going to go second calc maximum, step over here, and this, I'm going to guess that might be 2.6 repeating. And boy, I have no idea. I think I'm just going to round this one to 3 decimal places. So I'm going to go, since we're rounding, I'm going to say it has a maximum of 3.079 at x equals 2.667. That's a 7. Oh, sorry about the lack of focus there. Get that back in place. So 3.079 at the 2.667. If we rounded one, we'll round the other one as well. Okay, there's more to this section, but I'm going to come back. I'm going to wrap this one up now. We're already at the almost 35-minute mark. So stay tuned.